Welcome to today's Zeiss Expert Talk. My name is Oliver and I will be talking about the evolution of mobile optics. If you compare a photo taken with a smartphone just 5 years ago with one taken today with a state-of-the-art camera system, you can see the progress for yourself. I have been working in mobile imaging development at Zeiss for more than 15 years. As an eyewitness and engineer, I would like to give you a first-hand insight into the key areas of development: optics, lens calculation, manufacturing technologies and qualification. Lens flare and unwanted artifacts is one area where remarkable improvements in image quality have been achieved. I will show you how. And I will take you into the Zeiss Imaging Lab, where some of our development activities take place. In the end, you will have a better understanding of how smartphone optics are developed in reality, how we adapt conventional camera lens features for mobile optics in a small space, and the challenges we face. So welcome again to our topics for today's Zeiss Expert Talk. A time travel through lens development, flare optimization as an example of success, a tour of the Zeiss Imaging Lab in Oberkochen, and an introduction to iconic portrait styles. So let us start with the time travel to imaging. Imaging started with a hole, with a pinhole. The first camera was in fact a light-proof box with a hole in it. Just a simple hole where the light was projected through and the image was projected reversed on the back of the box. Due to this poor light sensitivity, the exposure time for those images were extremely long, and the people, if they wanted to take a portrait of themselves, they had to stand for minutes still and without any motion so that you don't get blur in these images. It was a very static kind of imaging and definitely not mobile. The next evolution in imaging in the cameras was introduce lens elements, and not just one but two. It was Friedrich Gauss who invented a doublet of lenses of two kinds of materials, of flint glass and crown glass with different properties, and by combining these two lens elements it was possible to reduce the chromatic aberration and also the distortion of the lens and to improve the image quality. And in optics, the saying, the more the better, is very, very true in many cases. Having these two doublets of Gauss elements, this was the birth of the first Zeiss Tessar lens in 1902. It was based on these two doublets and it offered for the first time outstanding contrast, distortion correction and color correction. And for the first time it was possible to reduce the size of the cameras, to make them mobile, and also reduce the exposure times significantly, to have more than these very, very static images. Due to this outstanding performance of this lens, it was given a nickname. It was called the eagle eye of your camera. And in reminiscence to this iconic lens, the modern Zeiss smartphone lenses are also given the name Tessar. The development of smartphone lenses started similar like with classical cameras. It was quite simple, having 3 or 4 lens elements and starting with very low resolutions. And similar like the classical cameras, there was this development, but now it was really somehow on speed. It was in time-lapse, where we needed more than 100 years for classical cameras. Here in smartphone photography, within 20 years, we went through all this development and I would say even further. So in 2004, we had 3 or 4 lens elements and 1 camera in the phone. And again, the more the better. We added lens elements more and more. Today we have up to 8 lens elements in 1 camera module. And about 2016, there was also the idea to add more cameras to a smartphone. Because for photography, you need more than just one viewing angle. Just think of landscape photography. So you need a wide viewing angle, you need a wide angle camera. If you think of portrait photography, you need a narrow angle for field of view. And and if you want to see some tiny details or far distance, you need a telelens. In classical imaging, you have zoom lenses or you change the lenses of your system camera. In smartphones, this is not possible. And therefore, this idea of adding cameras of different viewing angles was born. So in 2016 around, the first dual cameras appeared on the market. And then in the following years, we have seen triple cameras and today even 4 cameras in the back of your smartphone. And this is covering the ultra-wide, for example, for landscape photography, and also the telelens, which is going to zoom factors up to 10 times compared to the wide-angle camera of the phone, which allows to zoom in every tiny detail you want to see in your image. I have to stress again the saying, the more the better. There is one case where it is not really true. On every lens surface, you have a reflection rate of about 4 to 5%. So that means for a complete lens element, front side and back side, you have reflections up to 8 to 10%. That means 10% of the light is gone. But fortunately, there was a solution for this problem. It was known that modified optical surfaces can reduce these reflections, but there was no industrial process to do this modification. And it was in 1935 when Alexander Smakula, a Zeiss scientist, invented a process to apply thin coating layers on optics. And by applying these thin layers on the optics, it is possible to reduce the reflections dramatically. This was the birth of the T-Star brand. T was at the beginning, later on it was called T-Star, because this technology of applying thin layers was not developed and finished. It is an ongoing process. And after several years, there was an improvement by applying several layers, and then it was called T-Star. And this development is going on and on until today. Today we have coating layers that can reduce the reflections to 0.1, 0.2%, which means a lot of light coming to the sensor and also having very, very few reflections in the image. So this was a very quick run through history. But what are we doing actually? Let me start at the very beginning. The foundation for quality of a modern camera system is laid long before the hardware is built. And to develop and build a modern camera system, you need a network of partners. To create this network of partners, you have to qualify them, you have to assess them, to assess the production capabilities, the quality assurance, the quality management system, which is a very core factor, having a good running management system. And based on these assessments, to qualify the partners where necessary, to establish processes, joint processes that work seamlessly together. And after having these principles set up, then we have to go to the individual development of a device. We also have to start without building the hardware. We have to start much earlier. We have to define a specification of the camera system. We have to define quality limits. And also we have to create an optical design, which means the structure of the optics of these camera systems. And all this is done based on simulations. So let me start with the optical design of a lens. The optical design defines the structure of the lens and the properties of this lens. And some major properties I want to name are the contrast function, the shading, the distortion, and the chromatic aberration, which results in color fringes. These various parameters of the optical design usually are columns of numbers or graphs that are not self-explaining. Experts can to a certain extent analyze these graphs and have a glimpse idea if it's good or bad. But with the help of simulation tools, we can make close the gap between the graphs and the real image. So we can, for example, for the contrast function, for the contrast of the image, we can simulate real images and see how this contrast curve corresponds to the image quality. And then it's very easy to say, well, this image quality is good enough of the lens, or we need to improve it and have another development cycle before building anything. And it's a similar thing with chromatic aberration. Let me briefly explain what chromatic aberration means. So everybody of you knows the rainbow colors. That is because the light consists of colors, ranging from red to blue. By having a prism, you can split these colors and you see no longer the white light, but the colors. And a lens is nothing but an endless number of prisms put together. And therefore, also a lens produces these rainbow colors. That is something you cannot avoid. You have heard earlier with the Gauss doublets, there is a possibility to reduce that. And to know if the reduction of this color fringes is good enough, we also have a simulation that shows how strong these color fringes will be visible in the actual image. In this example, you have a real image where you can see these color fringes. The foreground shows purplish color, the background showing greenish colors. So this was about optical design and its analysis, and let me now come to T-star and reflections. There are many names for these effects and artifacts in the images. It's called flare, it's ghost, it's wheeling glare, and whatever. But in the image, what you see are circular artifacts, reflections, or these petal flares coming from the sensor surface. All of this is more or less disturbing. Sometimes you want reflexes like that because you have learned that reflexes belong to an image, but in most cases they are really, really unwanted. And this is where it comes into the game that we are using the T-star coatings to reduce them to a minimum. But what does it mean, reducing to a minimum? There we need to get a feeling, are the coatings that we apply good enough? And it's not just the coatings, it's also the mechanical surface. Is a reflection reduction of these mechanical surfaces good enough? Earlier in this video, I was also talking of T-star, the reflection reduction. So on the images here, you see some very typical flares and ghosts that you can see in images. You have radial structures, you have reflections, and you have this very typical petal flare that is caused by the sensor. These are not completely defined by the optical design. Partially, yes, but mostly by the coatings and surfaces of the lenses and the mechanical components. And also for this, we have developed a simulation tool. A simulation tool that can simulate the complete lens, including the coatings, including the mechanical components, and therefore we call it's a digital twin because all components of the camera are virtually existing in the digital world. And we can send light rays through the camera system at any stage, and then we can see every reflection in the image. And here in this example, you can see very good on these images the comparison of a real lens and the simulated image of it. And it's amazing how precise all the reflections, all the flare is visible already in the simulation. After looking at this theoretical stuff, here on these images, you can now see real images of devices. The first one you see here shows a device without T-star coating on it. And the second image here is the successor device with T-star on it. And you can easily see that most of the reflections are no longer visible in the image, and the remaining ones, they are reduced dramatically. So this was now a lot of theory and simulation where my colleagues are doing an amazing job. What you see now is quality assurance of Carl Zeiss in early days. Carl Zeiss used a hammer to smash optics where he was not satisfied with. You can imagine that this is not really suitable for modern times. And I want to show you in a short video what we are doing nowadays in a Zeiss imaging lab. So this is our imaging lab. For the qualification of a smartphone camera system, we are testing more than 150 camera modules. By doing this, we are capturing thousands of images that have to be analyzed. So the typical development process of a smartphone camera system consists of three phases: the engineering, validation and testing phase, EVT, the design validation and testing phase, DVT, and the production validation and testing phase, PVT. During all these three phases, we are testing more than 20 image quality parameters. We are testing more than 150 camera modules. And by doing this for every individual development phase, we are capturing thousands and thousands of images that have to be analyzed. The work in the Zeiss Imaging Lab is not just for qualification of smartphone camera systems, it's also for the development of technologies and features in general. And I want to point out two features that we recently developed for smartphone camera systems. The first I want to point out is the Zeiss Portrait Style. The Zeiss Portrait Style simulates the bokeh of the lens. A lens always has a background blur and a foreground blur, and the shape of this blur is individual for every lens, like a fingerprint. And in the past there were some iconic lenses like the Zeiss Biotar lens that produce a bokeh that is very unique and very typical, and many ambitious photographers and consumers want to have this typical look of classic lenses on their smartphone. Due to physical and optical limitations, it's not possible in a smartphone camera system to build a lens that produces these kind of bokehs. And therefore we have to replicate the look of these lenses by software. This is achieved by combining depth information together with the information of the optical design of this classical lens that we want to replicate. The depth information is calculated by the camera system of the smartphones, where we analyze the information of the different camera modules. Like the disparity of the eyes, you get 3D information with using two camera systems. And as Zeiss, we have access to the optical designs of these classical iconic lenses, and we can combine it. And there are several ways of doing these combinations. And here you see just some examples from where you can see the actual captured image, which does not show the bokeh. Some simulation tools like the PSF, it's called point spread function, or the ray tracing, which is a brute force method where you just calculate as many as possible image rays and then simulate it. And the last one you see here now is the simulation algorithm that we are using to replicate the Zeiss Biotar lens in a Vivo smartphone. The second feature that we also developed, I want to point out, is color correction. Zeiss has a huge expertise in color and color correction due to its product portfolio. We have medical devices where it's crucial to have the right colors and also microscopes. And in our division, we have the cinematography lenses where we have color matched lenses, where every lens has to produce exactly the same color like the other ones. And the challenge is to merge the color perception of the brain with the color rendition of a smartphone camera system. This is a very challenging process because it's not just transferring values and numbers that we can measure, it's always also transferring memory colors where the brain says it has to be this color, like green grass or maybe the red sports car, where your brain is saying it must be that color, even if it's not necessarily measurable exactly this color. This topic of color correction is very complex and interesting, and I would love to recommend to you to watch our other expert talk with David, who is our expert for color rendition. So what can we conclude for today's expert talk? We had a short time travel through lens development, from classical lenses to modern smartphone camera systems. You gained insights into development and qualification of an innovative camera system. I took you to my workplace, the Zeiss Imaging Lab. I hope I could give you some insights that were new for you. And I hope this helped you to better understand our enthusiasm with modern imaging technology. Thanks for watching. Stay tuned for new developments.